All right, welcome ladies and gentlemen. This is the pre-lab video for the molecular weight of a vapor lab. This is where I'm going to describe how you're going to do the calculations for this lab based on the measurements that you're making. So this lab is called molecular weight of a vapor, which means you're doing exactly that. You're finding molecular weight or molar mass or gram formula mass. Basically, remember, we have all these interchangeable terms in chemistry that all mean the same thing of a gas. And you have to create the gas. You've got three liquids to choose from, three volatile liquids, which means that they evaporate very, very easily and they turn into a gas easily. You're going to figure out their molecular weight. The key to understanding how to do this is remembering that molecular weight, the unit for molecular weight is grams divided by moles. That's it, grams per mole, which means that there are two components of molecular weight. There's mass and there's moles. And if you find out a way to get mass and you find out a way to get moles, you simply need to divide the two, grams divided by moles, grams per mole, to get the molecular weight. So really, we're breaking down these two values in this lab, grams and moles, and you're going to determine each of them, and then simply divide your mass by your moles to get your molecular weight. So mass in this lab, as is typical in almost any lab, is going to come from a balance. So you're simply going to put your sample on a balance to get the mass. Now the balance that we're using goes to 4 decimal places, and I think it's the first time this year that we're using that particular balance. So I'll talk a little bit more when we get in the actual lab about using it. But it does go to 4 decimal places as a very special balance. We need that because gases don't have very large masses to begin with, so we need something that can be very precise. So 4 decimal places. And this is after you vaporized it. So you need the mass of your empty container in order to determine the mass of your gas within the container. So that's the whole example. It says it says to do this in the procedure. Just make sure you do that. You need the mass of your empty container first before you put anything in it, so that you can subtract away the empty container to get the mass of just the gas. Now moles, we don't have something that can measure moles directly. Moles is something that we have to calculate in chemistry because mass of moles will change based on what substance we have. So we're going to get moles from PV equals nRT because the N component is moles. So we're going to talk about how we're going to get moles from PV equals nRT. So we're making this a little bit bigger. We are going to be measuring basically every single component of PV equals nRT except for moles. So we will be solving for N to then use in molecular weight calculations. Pressure, the first bit. Pressure we are going to get from weather.com. So we are going to assume that the pressure in Webster is the same as the pressure in the lab room, which is a fairly safe assumption to make, that whatever pressure Webster is under is also the pressure that the lab room is under. But big thing about this, when we get pressure, this is the pressure that the weatherman or weatherwoman talks about on the news every night. It will be in inches of mercury. So right away, that should tell you that you're going to need to convert it, and you're going to need to convert it into one of the 3 units that we use for pressure, either atmospheres, torr, or millimeters of mercury. And I'm not going to tell you how to do that, so you need to be thinking about that, and I don't want to see any direct conversions. So I need to see individual steps, so you can't just go to Google and have it converted for you. No, I need to see the dimensional analysis from you that shows how you're going to turn inches of mercury into one of the 3 units that we use in AP Chem. Volume, because we need volume. Volume is going to be the volume of your 125 milliliter Erlenmeyer flask. Here's a secret. The volume of your 125 milliliter Erlenmeyer flask is not 125 milliliters, so you cannot put that down. The 125 milliliters in the name of the flask means that that flask is designed to comfortably hold 125 milliliters of liquid, which means that its volume is actually more than 125 milliliters. So this is you're determining volume through that whole final step where it says to fill your flask with water, and then completely, and it's got to be completely filled with water up to the tippy top, and then pour the water into graduated cylinders to determine the volume of water. So that's how you're going to get the volume of your flask. You cannot tell me that's 125 milliliters because it isn't. It will be more than 125 milliliters. N is what we're solving for. R, that's a constant, so that's easy. That's on your reference table. And then T, that's temperature. Again, we're talking about the gas here. We're trying to vaporize a gas. So the temperature will be the temperature that we hold the gas at. And this is not going to be room temperature, because what you're doing with your gas is you're putting it in a hot water bath. You're boiling the water, and that's going to cause the liquid to vaporize. So this is going to be the temperature of your hot water bath. Now, you are boiling your water. Again, though, do not assume that the temperature of the boiling water is 100 degrees Celsius on the dot. There are a number of factors that can impact that. So you do actually have to measure with a thermometer the temperature of your boiling water. So it should be boiling when you do this, but don't assume that it's 100. So when you do that, when we get the pressure, the atmospheric pressure in Webster that day, when you determine the volume of your flask, when you measure the temperature of your boiling water bath, you use the R value from your reference table. You can get moles, solve for N, which then gets plugged back into grams per mole, and then there you go. That is how you get molecular weight. So you're going to be measuring P, V, and T. You're also going to be measuring mass, and through all those things together, you can get molecular weight of your vapor. Now, there are going to be 3 unknown vapors. You're not doing all 3, you're only doing 1. Some procedural comments on the lab. This is our setup, right? We have our stand with our Bunsen burner, and you are going to clamp your flask in place. This is a big point. The lab says for the hot water bath to basically fill up the 600 milliliter beaker with water. That is a procedural change. I made a note on the front cover. You only want to use about 350 to 400 milliliters of water in that beaker, because you need to be able to comfortably fit your flask in it. So if you totally fill the beaker up with water, then you go to put the flask in it, now you're going to have boiling water that's pouring off, and that's not so hot, or pun intended, it's actually very hot, and that's a problem. When you measure the temperature, right, you want your thermometer, right, to be in here. We're assuming that whatever temperature the water is at is the same temperature that the flask is at. Notice that we have a pinhole in the top of that little cap. The procedure says that, right? You make a little pinhole, and that's to ensure a number of things. First of all, you never want to heat a closed container, because then you have a buildup of pressure, and then you have a possibility of it breaking and exploding, and that's bad. And secondly, we want to make sure that all of the air gets out of the flask. All 3 of the liquids that we're using their gases are denser than air. Air, on average, because it's mostly nitrogen, that tells us something that basically it's going to be around the same density as that of nitrogen. All 3 of these volatile liquids that today, they'll produce a gas that is more dense than that. So basically, that pinhole is to help us get rid of the air, get rid of the N2, get rid of the O2, make sure that we're eliminating all the other trace gases as well, so that the only gas that's in our flask is the one that came from the liquid. So that pinhole is very important. And again, huge point that I cannot emphasize this enough. You want to check your flask after 5 minutes. Because the lab says that it could take between 20 and 30 minutes to vaporize the liquid. Patently false. If your water bath is at a full boil when you put your flask in, which it should be ideally, you should want to put your stuff in there like only when your water is boiling, then it will not take long at all to vaporize your liquid, and I mean really like 5 minutes. The longer you let your flask sit in the boiling water bath after it's vaporized, the more gas you're going to lose. Because if you keep on increasing the temperature of those gas particles, they're going to be moving faster, and you will increase the likelihood that they will find that pinhole at the top of the flask and then therefore escape. So you really, really, really want, as soon as your gas is totally vaporized, that's when you want to start thinking about taking it off. So start checking after 5 minutes. If it's not totally vaporized after 5 minutes, meaning you take it out of the boiling water bath, you wipe the bottom off, you look in, you see that there's still some liquid there that hasn't vaporized yet, no big deal. Put it back in. You haven't turned your boiling water bath off. It's still on. And just let it sit for another few minutes and then check it. So those are the big points that I have. Come see me if you have questions. Again, we're doing this on Friday, and use this video for when you're doing the calculations for determining the molecular weight of the vapor.